Well, it looks like we can start officially. Welcome back, everyone. Looks like a pretty small class today, which is kind of surprising, but I think we were talking about that earlier in class. Usually this class runs as a night class and it might have higher attendance because of purely that reason. It's kind of interesting that we're doing it as a earlier class. I guess it has pros and cons to that. There might be an enrollment issue for this class running at this hour. But either way, it doesn't matter if just a few people are here, we're going to get through the same kind of material. And I know personally, if I was a person in this class, even if I was coming on the Zoom side, I'd probably be logging in right at the minute. I guess I'm just that kind of person. But welcome everyone back. If you just joined the class, if you registered, say, yesterday or just today, the first recorded lecture for our Tuesday's class is posted here. And we'll be getting in the habit of recording all classes and posting them. Other just quick announcements I have is that we're on week 1 and we have 15 weeks to go, but now you have a good feel of what class is going to look like, how it's probably going to fit in with the rest of your schedule with school, work, home life, and those kinds of things. The best thing to think about right now across the weekend and coming into next class is how are you going to fit in a routine of getting in the reading for the course, the studying, the reviewing, those kinds of things. Try to work out a schedule, sometimes putting down just something on notebook paper, maybe an Excel schedule, something like that, is a really good idea. The more you stick to it, the easier it's going to be to get in a routine that just works for your weekly life. And aside from that, I do have some extra videos posted here. These are really quick applications on some of the power of systems of linear equations, and they can be pretty surprising, different kinds of applications. I would consider these are more the typical ones. If you're a fan of chemistry, you might have noticed that balancing a chemical equation does get equation heavy, and linear algebra can very naturally enter that. If you're more of an engineering electrical circuit kind of person, this is a tougher video, but let's open this one anyway. We're not going to watch the whole thing. I put a timestamp on there for my reference. But here's what another system of linear equations would look like in a typical application. Once I click on all that stuff. So this is an application of Kirchhoff's law. And oh, what in the world? I forget that there's ads on this. I'm going to try not to open too many of these videos because I'm not trying to support any of these people. I guess I got a skip button. Okay, finally. So this is a circuits diagram. Lots of interesting notes have been put on here. Oh, wow, this is harder than I thought. This might be easier to actually see on your own time at home. Somehow my buttons here are not working the way you would have expected. Oh, it's just went to the next page. There we go. So this is the circuit diagram. So if you've looked at those kinds of things before, looked at Kirchhoff's rules before, we're balancing voltages in, voltages out, and it leads to several equations you would have to solve, and naturally to a system of equations. This looks a lot different than the ones that we've been writing, but just think of the I1, I2, I3 as being, say, an X1, X2, X3, like in this system here. This one just goes off to X4. So if you'd like to take a look at those kinds of applications, if those are interesting to you, I'll be posting them as we go from section to section. There's a lot of great content out there. Hopefully you have an ad blocker on YouTube. That makes the experience a little bit better, I think. They're always going to be purely optional. The major content of the course is always going to be contained in the notes. And one of the reasons I do this kind of thing is that there's a lot of great applications to linear algebra, but we also have a tight schedule. We have a lot of material to cover. If we're going to do an application like electrical circuit, we also have to cover Kirchhoff's law in the first place. And sometimes it's easy to go way off track when we get behind on the actual linear algebra content. So in a lot of cases, I'll just be posting applications like this to give you an idea of the use case and stuff like that. They'll always be purely optional, but sometimes pretty interesting. And that's my 5-minute spiel to start us out for the day. Any questions or comments from you all so far? Okay, well, welcome back, everyone. Looks like the Zoom class filled out. Good to see you all made it in. And here's where we left off last class. Let's take a look at this just briefly once more to refresh ourselves. It's not like the system of equations we were looking at before. This one's just a little bit more simplified, so we can focus on some of the main ideas that we're going to be working on primarily today. What we want to do is solve larger systems than this one in a way that's not going to be so algebraically painful like these kinds of methods might be. The major ideas we're going to use is we can do a row replacement. Row 2 is replaced by a linear combination, row 2 plus row 1, of other rows. We can also do a rescaling of rows. We can just simply divide a row by 2. This is another row replacement. Row 1 is replaced with row 1 minus row 2. And we can do other things. If we really wanted to, we could interchange two rows. It's the same as changing the order of equations. It won't ever affect the solution set. And so those are our main rules. Yeah, go ahead.
And just because I was thinking about it, so are you only allowed to change or affect one row at a time? Does that make sense?
Yeah, absolutely.
Okay.
So the question was, are we only allowed to change one row at a time? And the answer to that is no, you could actually do multiple row operations all at once. So we could have, say, done this one and also did row 2 divided by 2 all at the same time, all at once on this operation right here. So you can do many row operations all in one fell swoop. Is that the kind of question you're asking about on that one?
Kinda, and like you can't, and I guess it kind of makes sense, but you wouldn't be able to change like row 1 at this in the same step that you changed row 2. So how, like what we did at the very bottom, row 1 is equal to row 1 minus row 2. We couldn't do that at the same time that we did.
I gotcha. Yeah. It turns out doing this row operation and this row operation at the same time, we wouldn't be able to do that one necessarily unless we were really, really careful, because this row 2 right here is not the same as this row 2 over here. It changed by this row operation. So these operations became nested inside each other.
So just
You could do it, but yeah, you'd have to keep track of how all the nesting of those operations were going on at once. Other questions at the moment? Okay, so this was kind of our buy-in example of why we want augmented matrices, matrix operations. And here's our rule book of what we can do to an augmented matrix that does not change the solution set. We can do a row replacement. That was this operation right over here. Row 1 was replaced with row 1 minus row 2. Replace one row by the sum of itself. Row 1 is replaced by itself right here, and a multiple of another row. So this is row 1 plus -1 times row 2, if you want to think of a sum of itself and something else. We can interchange two rows. Again, that's just like swapping the order the equations were written, so that's always completely fair game. And we can rescale an entire row by multiplying by a non-zero constant. That was this operation right here. Non-zero turns out to be important because if we multiply a row by 0, it's like deleting an equation. It's changing the solution set in a fundamental way in that situation. So those are our 3 row operations that are on the table. We follow all 3 operations. We say that our matrices are not equal anymore. We change the entries, but they're row equivalent. And this is the tilde symbol that we've been writing all along on the last problem. Whenever 2 matrices are row equivalent, we'll write matrix A is row equivalent to matrix B. That's kind of a funny thing to write so far with the notation. Usually if you're thinking of a scalar, like an ordinary number, you write x is 5. But if you're writing down a matrix, this would be considered a non-scalar object, and we often use capital letters at the start of the alphabet. Not exclusively, but generically that's what we would be doing if we're indicating a matrix as a variable, much like x equals 5 for a single number or scalar. We'll later call these things. Then this is the massive theorem that we were hinting at. Well, I shouldn't say massive, really important theorem we were hinting at. If we do things just right, then we never change the solution set. We have the same solution, a unique one, 1, 3, over here and over here. You could take these operations in different orders, but as long as you're always just using those operations in any way that makes the most sense to you, you'll have the exact same solution set. So that's a natural and wonderful theorem to have. It tells you essentially all roads lead to Rome. These are the ways you'll get there. Everyone ends at the same exact solution set. So our job is really just to practice with these row operations. Since these are brand new, we'll take them along with us as we practice. Let's put them down below here. And example 4 says, write out the system of equations that corresponds to the following augmented matrix. Then solve the system. That seems like a weird problem because, well, this is ready to go. It's told us it's an augmented matrix. That means we could put some dots here if we'd like to really emphasize the right-hand side is the equation equal to 9 in row 2, equal to 9 in row 1. I said that in reverse order for some reason. And some equation equal to -2 in row 3. But this equation is really just more about, it's important to know how to transfer your system of equations into an augmented matrix form. And it's just as important to know how to go the opposite way. Take what you've got and write out the system of equations. Sometimes this alone could be an exam question. My exams that I write in linear algebra are long number-wise. It's going to be anywhere between 16 to 20 questions, but that's only because there's a lot of small concept questions. This could be just a bona fide question on exam 1. This is all we would have to do. Recall that when you look at this augmented matrix, column 1 is corresponding to the variable associated with x1, likewise for column 2, likewise from column 3. So if you'd like to add a little bit just extra notation, it never hurts. So now row by row, row 1 says 1 times x1, or just x1 for short, plus 2x2 minus 2x3 equals 9. And we do just the same kind of idea on every single row. In other words, when we see this augmented matrix, this is what we're dealing with really in the back of our minds. We're dealing with a system of equations in this form. So it's translated again. Row 2 says 2x1 plus 5x2 plus x3 equals 9. Another thing that's interesting getting used to in linear algebra is subscripting is everywhere. Sometimes I get a little mixed up on my subscript. So if you notice I wrote an x3 here when it should have been an x2, let me know right away and I'll get it corrected. Then finally, last row is that x1 plus 3x2 plus 4x3 is equal to -2. So that here is our system of equations. Any questions with doing that transfer? Okay, the problem kind of feels like a backwards problem in a certain sense, right? Most of the time when we're doing this kind of thing, we're going to start with the system of equations or just the augmented matrix and just proceed through the steps that's going to lead to the solution. So this one went backwards at first just to practice that skill here in the reverse order. Now we want to actually solve the system. And again, it seems kind of strange. We're not going to solve it over here, not because it's impossible. It absolutely is. It just takes lots of paper and your hand is probably going to get tired by the time you're done. It's easier to just solve it over here using the elementary row operations. So let's start this out in earnest. A, which is an augmented matrix, let me just rewrite it. It's getting a little too busy above, is 1, 2, 1, 2, 5, 3, -2, 1, 4. I'll write this in just as a personal reminder. It's augmented with 9, 9, -2. Not all matrices we deal with are augmented, so this is sometimes a great reminder that you're not dealing with just an ordinary matrix, but a system of equations is working in the background all at the same time. Now here's the next idea that we're going to really focus and make more precise in section 1.2. The idea is pivoting off the right pivot column and the right pivot entry. What I mean by that is in the far upper left corner, this number 1 right here is our pivot position. Linear algebra is about obtaining a lot of zeros. That's kind of what we did on our first example in the notes. So we're going to pivot off this entry, use these elementary row operations. This is usually the big one we use quite a lot, to obtain a 0 below. This -2 has to vanish, and this +1 needs to go away as well. So we're going to do a row operation. We're going to say our matrices are equivalent. And so that's the tilde right there. Original matrix A we cannot put an equal sign, that's algebraically false. We'll just say is now row equivalent to this new one. First, let me show what we're going to try to achieve. I want to eliminate that 2. So my goal is row replace row 2. We write row 2 gets row 2. That's replace one row by the sum of itself. Here it is. There is itself again. And a multiple of another row. The multiple is going to be -2 times row 1. Why -2? Well, if we multiply row 1 by -2, add it down below, that entry vanishes. And that's pretty much our whole goal, get loads of zeros in this matrix. So let's go 1, 2, -2, 9. Row 1 copies in unaffected. This syntax here is saying we're just changing row 2. So this takes a good bit of eyeballing things, a little bit of arithmetic. Take -2 times this row, add it to the entry below, and that's -2 plus 2 for a 0. This is kind of hard to track if you're not used to seeing this with your eyes, so let me go carefully. -2 times this entry, added to the entry below, is -4 plus 5 for a positive 1. And then just keep on following those instructions. -2 times -2 is positive 4. Add the 1, and we're up to a 5. Follow the red dot to track the way this is going. Again, this could feel like synthetic division in a lot of ways. -2 times this 9 is -18. Add the positive 9, and we're at -9. Let's pause right there before we go too far on this one. This is one of the key fundamental things that we're going to be doing in linear algebra. Lots of row operations. It's something we have to do on exams, so I ask you to show steps as well in the homework so that you get that practice, and I can provide you with direct feedback to help out on exams. But how does this look so far to everyone in the class? Did it make sense how we got this row? Awesome. People look to feel pretty good about it in class. How about for folks over Zoom? Did that make sense on how we produce row 2? The new row 2, rather. Awesome. If anything ever looks weird on the numbers here, don't hesitate to interject at any point. Sometimes I just made an arithmetic miscalculation. It's Thursday, basically the end of the week, and it's arithmetic that's the first thing to go when you start to get tired with math and in a math class. Thanks for the feedback, everyone, so far. One thing I should put out, just for the sake of the notes, is sometimes, especially when you're learning this, it's not a bad idea to visualize it this way. This row operation was, in its shorthand, taking, let's say, -2 times this to get -2, -4, positive 4, -18. Add to the row 2, which was 2, 5, 1, 9. And if you tallied all that, you get 0, 1, 5, -9, which is what we duplicated right here. The reason I don't do this very often is that's a lot of scratch work and it takes a lot of additional time. But when you're learning it, it's not a bad idea to do just to get your feel for how this all goes. So this is the scratch work that produced that column. Let's keep on going. Our goal is to remove this 2, force it to be a 0 is what I mean by removing it. We want to force the entry below the pivot circled in orange above to be a 0 as well. And this was not so bad, just another row replacement. This time row 3 is replaced with itself, row 3, minus row 1. So all we're doing is taking -1 times row 1, adding to the entry below. So carefully visualizing this, that would be -1 plus 1, producing a 0, -2 plus 3, producing a 1. Now positive 2, -1 times -2, sometimes I get mixed up on the negatives here. Add the 4 for a 6. -9 minus 2 takes us down to -11. So far so good. We achieved our main goal. We have a pivot here, zeros down below. Our objective is to fully solve the system. So now we start to do a staircase-like pattern in our matrix. Later on, we're going to call this a type of echelon, which is a German word for staircase. So it's same way to say the same thing. What I mean is go down just one row and move right until you hit the first non-zero entry right here. Circle this one again. And for that next pivot position, we want to eliminate entries this time above and below all at the same time. So what has to go this time is the 2 and the 1 in those positions. So let's work this out carefully. I ran out of space to the right, so I'm just going to write my tilde over here to say prior matrix, row equivalent to the new one. I'm happy with just row 2. This is the only row that's going to remain unchanged. So let's copy that in first. 0, 1, 5, -9. Now let's go for the entry above. Again, you might be doing this in a different order. As long as you're following the row operations down below, you're going to always get to the same result. So first thing I'm going to do is remove that row 2, that 2 in row 1. So that means row 1 gets replaced with row 1. Now what do we have to do? Just look at the pivot. If we multiply that entry there by -2, add it above, we get our 0. So that tells us the ingredients or the recipe or the algorithm. Take -2 times row 2. It's going to be added to row 1, or said differently, row 1 minus twice row 2. So take -2 times this, we'll get a 0 above. But you notice I kind of skipped the entry over here. Because it's a 0, nothing happens. It doesn't matter what I multiplied it by. When I add it to row 1, there's going to be a 1 above. And likewise, there has to be a 0 below. Nothing's going to change because of that 0 right here. So we really start off on column 2 over here. -2 times this entry added to the entry above gives us a 0. Repeat. -2 times here is a -10, -2 for a -12. Repeat again. -2 by -9 is 18, plus 9 for a 27. And row 1 is satisfied. We're going kind of slow because, again, it's a lot of numbers flying out of nowhere. And we're just mainly focusing, what does this pattern look like? We're developing our muscle memory for our row operations, essentially, with this example. Any questions at all, folks, with that brand new row 1? Okay, let's go back to this entry right here on the prior matrix. We want to eliminate the entry down below. That's one that's not so bad. They match up. So all we have to do is take the following. Where the red dot is, that has to eliminate. So we're affecting row 3. We'll write row 3 is going to be replaced with row 3, just say subtract row 1. So that will be -1 plus 1 for a 0. Subtract row 1 just means multiply row 1 by -1, add to the entry below. So that's -5 plus 6 for a +1. +9 now, watch the double negatives, -11 gives us down to a -2. So far, we started right here. That was pivot 1. We moved down and right. That's our second pivot. We move down and right again. Sometimes on bigger matrices, we might have to move right several columns before we hit the next non-zero entry, but that's our third pivot. Yeah, go ahead.
For the last one,
Yeah,
I mixed up. I got -20. I just messed up my signs.
let me take another look. That could have been me. There's a lot of arithmetic happening out here. So I was taking row 3 minus row 1, and I had -1 plus 1 for a 0, -5 plus 6 for a +1, and then -9 for +9 minus 11. Yeah, that would again gotten us down to the -2. That's something that mixes me up all the time with this kind of stuff too. And I mean, full disclosure on these notes, before I even come to class, when I wake up probably around 9 a.m. or something, this is the first thing I'm doing is I'm practicing these same exact problems just to make sure I know how it goes, kind of refreshing myself on the arithmetic. And I'm not spectacular on arithmetic, but one thing you'll find is you get better at this kind of arithmetic and when you take a linear algebra class. Really big side benefit. But other questions so far?
So you wrote row three minus row one instead of minus row two, I believe, on the last
Oh,
part.
good catch right there, Austin. I said minus row one, but if I did that, you're right. That would have gotten us a negative 20. So you were absolutely right in class, and you're absolutely right as well, Austin. That is a subscripting error right there. It should have said, let's use the correction pen, row two, not row one. So that makes the confusion make a whole lot more sense. Sorry about that confusion there. And again, that's another thing I was mentioning earlier. Watch out for those subscripts. That's another thing that's kind of interesting about our linear algebra class. We have probably already written about 100 subscripts already if you're really keeping a tally on these. Other questions or comments at the moment? Okay, these little instructions here are optional, but I have to also say, if you're going to get in the habit of using them, be careful with them too, because they could cause more confusion and do more harm than good. So I'll try to be more mindful of writing these out as carefully as possible as well. But now we have an interesting echelon form. This is a nice set of pivots, and all we now need to do to fully solve this system of equations is eliminate the entries above. We already know that x3 is equal to negative 2 if we transfer out this column, and we can start making substitutions working backwards. Let's in fact just more efficient to finish out the row operations. In fact, the only elementary row operation we've used so far is replacement. We've just used this one over and over again and produced 4 zeros. We want 2 more. So here's the next set. Row 3 is as good as it's going to get. Well, we're going to start by copying that one. 0, 0, 1, negative 2. I sense this is our last operation, so I'll bring back the notation that says augmented matrix. Here we're going to be transferring in our answer. And now there's the moment of being really careful with what we mean. Let's do our row operations. So go back to the last pivot formed. That 5 has to go away. So the instructions should read, row 2 gets replaced with row 2 minus 5 times row 3. So we'll have a negative 5 plus 5, getting us a 0. But another thing we mentioned is we multiply these zeros by negative 5. Nothing changes out here. So some people, before you even get started, might copy in the entirety of column 1, 1, 0, write the entirety of columns 2, 0, 1. And that's a good idea because now you're just focusing on these 4 entries. That's the only thing that's going to change now. So the operation is negative 5 times row 3 added to this row 2 element, 0. Negative 5 times negative 2 is a positive 10, minus 9 for a positive 1. Then repeat. We want to eliminate this negative 12 here. This means row 1 is going to be replaced with row 1, and just add 12 copies of this row 3 entry back up to row 1. So that means plus 12, row 3. So working that out, 12 minus the 12 here gives us a 0. Negative 2 by 12 gives us a negative 24. Add the 27, and we're up to a 3. And this is what we'd like to see right here. This matrix is actually really special. Let's put down just a side comment. I equals 1, 0, 0, 0, 1, 0, 0, 0, 1 is the 3 by 3 identity matrix. When we do matrix algebra in chapter 2, this is like the number 1. This matrix multiplied by any other 3x3 matrix or any other appropriately sized matrix, we'll spend more time on that, won't change the matrix. So it's like multiplying by the number 1. In the context of a system of equations, it also means we have a unique solution. Let's bring back the x1, x2, x3. It's optional, so that's why it's written in orange. Anything pretty much in orange is just an additional comment or an optional additional thing to put on the notes for clarity. But now row 1, if we were to transfer this back to a system of equations, exactly like we did at the start with matrix A, row 1 would say x1 equals 3. Row 2 says, well, 0 times x1, if we say it verbatim, that's just a 0. 1 times x2, which is just x2, plus 0 times x3, which is 0. The dot, dot, dot means equals to a 1. And then finally, last entry is just saying, more briefly, x3 equals -2. So now we have a unique solution. And the system, let me get that letter E to look right, is consistent. Well, we did it, folks. We took something that's, again, if you're really good at solving a 3x3 system like this by hand, popping down x1, x2, x3, you might have solved it in the same amount of time that we did. But I promise you, you wrote a lot more than we did right here. This is a very efficient way to get to a solution set. Well, this is really our second run at practicing row operations. We're going to look at a couple more on these notes and also look at other weird things that can happen. Sometimes there is no solution. Sometimes there are infinitely many solutions. We'll see some of those issues on these notes and the next set of notes as well. But any questions or comments, folks, on solving this first big system? Okay, so far, this is the linear algebra experience. There are loads of definitions, loads of really technical theorems, some of them with like 20 parts in linear algebra, the infamous one being the invertible matrix theorem. But just about everything we explore, no matter how technical and deep, a lot of it happens to be organized by pivot positions, doing the right elementary row operations to reveal zeros in your matrix. So this is like the core fundamental computational technique we'll be using the entire semester, with some exceptions. Some sections are just a little bit different, like our last chapter. But let's try this out again. Example 5, we're going to do the same sort of thing. I should rephrase that. Example 5 actually is a little bit different. Let's focus on the difference in the instructions. Example 4 said, write out the system of equations, then solve the system. Over here it says, just determine if the system is consistent or inconsistent. This deserves a comment immediately. If we are solving a system, we need zeros above and below all pivots. So that's what we were doing in the prior problem. The moment we circled a pivot position, like the one right here, we said eliminate the entry above, making it 0 and below. Here, there are only entries below. Here, there are only entries above. And that's what got us to the identity matrix. We needed that because we were looking for the exact solution. However, these instructions are different. They're not asking for the solution at all. And that means there's a huge speed up on this. Here's the second comment. If we are only determining if the system is consistent or not. Let's review our terminology just briefly. If you're saying the system is consistent, that's just a different way of saying it has a solution or infinitely many. If we say a system is inconsistent, that's just a way of saying no solutions. So if we're only determining if the system is consistent or not, we only need zeros below. I should say all, again, to match up the parallelism there, below all pivots. So that can save you a lot of time in homework problems, potentially an exam problem as well, because is what this is about. You could go above and beyond an exam and actually solve the whole thing, give me the solution set, but that's not the major drive of the question at all. All we're asking on this problem is, can you find a solution? Well, let me say that better. All we're asking about in this problem is, does a solution exist? We're not asking what the solution even is. And it turns out that's a regular question to ask throughout the semester. That's the fundamental questions about linear system. We often wonder, without even knowing the solution, sometimes the solution really is irrelevant to the larger picture. We just want to know, is it consistent? Does it have a solution? And if we do say it's consistent, we also want to know, is it unique or are the solutions infinite? So that's going to change our operations a little bit when we go to solve this one. We're only doing the statement in purple. We only need zeros below all pivots. But I'll continue to circle pivots in orange just to maintain that pattern as we go through the notes. Well, we're ready to give this one a start. Any questions or comments first? Okay, an arrow could also help here. Because of this question, we're going with that comment there in purple. Okay, this one is now a 4x4 system in the sense that there are 4 equations now in 4 different unknowns. So it's a little bit bigger, and it's a little bit trickier to write in because notice the formatting is kind of off. Some people might rewrite this and put x1 over here in its own column, but let's see if we can just transfer this over just by visual inspection. That's a pretty decent technique on its own. So here's the augmented matrix that belongs to the system. So column 1 is going to be associated with x1, and the technique is simply pull coefficients. So for x1, row 1, we have 1 for a coefficient, but what should we put straight down below here for row 2? Anyone see the value? Yeah, absolutely. We should just go with the 0 as you indicated. If there is no x1, well, that's just a shorthand. There really is. It's 0x1 like that. It's just that we didn't have to write it in. It simplifies back down to this format. So everything really has a coefficient, whether it's visible or not. Coefficient here is -1 for x1. No x1 on this row means put in a 0. And then rinse and repeat. Next column belongs to x2. So very carefully pull those coefficients. They go -6, +1, +6 below, and -1. x2 wasn't as bad because x2 appears everywhere. It's just the formatting that's a little bit off. And I kind of regret my spacing here. Let me see if I can fix this. Oh no, looks like it's attached. Let me see what I can do here. I want to just bring back briefly. Oh no, there we go. I want to bring back the x1, x2, and so on, just because it's still helpful to visualize. So this is coefficients from x1, x2, and for x3, we'll pull, well, from row 1, if there's no x3, we throw in a 0. Then it's this -4, +1, and 5. Let me know if I just mix up a coefficient. It's very easy to do. And by the way, with these linear algebra problems we're doing, the ones in the notes and the ones in the homework, sometimes you get a really big hint that maybe you just copied something down wrong, because a lot of these numbers are designed so that if fractions occur, they're not nasty. And a lot of times there's no fractions at all in the operations you take. If you're starting to get something like 1,743 divided by 972, you probably made a mistake somewhere. The numbers are rigged to be kind of nice. So we focus more on the linear algebra, not on painful arithmetic at every single step. And that'll be true with exams as well. But now for x4, go 0, 1, 5, 4. So that forms all x4 coefficients. They'll be augmented. So now we bring in the right-hand side where the red dot is, 5030. All that's left to do is start our row reduction. And again, we're only looking for zeros strictly below the pivot entries from that comment in purple. This is the very first pivot position, the upper left corner. That's not true for every matrix, but a lot of the matrix, probably like 99.9% of our matrices, has this feature. Your pivot is on the upper left. There would have to have been no x1 whatsoever for that not to be the case. But it turns out that's kind of an unusual system to write down. It'll happen eventually way down the line in eigensystems, eigenvalues chapter. But let's start reducing this. Notice this one's not too much work on the x1 column. All we have to do is eliminate that entry on the red dot. That's going to be a row 3. So row 3 is going to be replaced with, we can just take row 3 plus row 1. That means row 1 stays the same. Let's copy it in. 1, -6. 0, 0, 5. Then it also means row 2 is the same, so copy that in, 0, 1, -4, 1, 0. Now take row 1, add it directly to row 3, and replace row 3 with it. Just write the resulting sum. Going entry by entry, we'll have a 0, 0 again, a 1, then a 5, and then an 8. So all I did is directly add together row 1 and row 3 entries, writing them down into this new row 3. Now finally, nothing happened to row 4. That's the only operation we had to take. There's already a 0 in this position. So copy in row 4 as 0, -1, 5, 4, 0. And on to the next step. Okay, this actually takes, or for these kind of problems, penmanship is actually a pretty good benefit. The better you get at writing kind of block linear way so things don't get skewed like I did it here, the actually easier it is to get through. Sometimes I made mistakes just because I was writing weird and diagonally and it got mixed up what was in what column. So if that ever happens to you, just try to practice. I don't want to say it this way, but the more you write like a robot, the easier it is to kind of just organize things together. So next thing we do is we analyze the pivots again. This was our pivot position. We move down just once and over to the right. This is our next non-zero entry right here. We still haven't needed to do anything like interchange rows, but more of those kinds of things will be coming up in the next section. With where we're at right here, we just want to eliminate strictly the element below, that -1. So let's write out our operation. The thing is changing is row 4 now on that entry. So row 4 will be replaced with row 3 plus row 4. That means this is a lot of copying. Only row 4 changes. Let's just do the busy work, get it out of the way of copying in both rows 1, 2, and 3, the non-changing rows. 1, -6, 0, 0, 5. 0, 1, -4, 1, 0, going row-wise. 0, 0, 1, 5, 8. Now we take our operation. Take this row. Hang on, let me take a look at my work again. That's a mistake, isn't it? I should have said row 2 added to row 4. Let me correct that subscripting right there. Let me just X that out. Row 2, actually, that's kind of hard to read in the notes. I'll just write in this way. It's a good thing to be really careful of. Usually I don't catch my own errors, so I'm feeling kind of grateful for that. But if I find an error, that's sometimes an indication something else might be off. Does everything look all right to folks so far? Okay, now we knew what we were doing. I just wrote it down wrong right here. Take the row 2 entries, add it to row 4, replacing. We'll get a 0 here, and now it starts where the red dot is. 1 plus -1 is 0. 5 plus -4 is going to be a +1. Then a 5. And then an 8. Okay. Somehow I feel like I made a mistake somewhere. Oh yeah, I looked at that hate and I copied it down. Thanks for identifying that. It just didn't look right or feel right at the moment. Let me try this again. I'm supposed to be on row 2, adding to the entries below. So I made it from here to here, here to here. 1 plus 4 is a 5. I think that 8 just distracted me for no apparent reason. 0 plus 0, the row 2 plus row 4 entry, gives us that 0 there. Thanks for spotting that. Now at this stage, this is how I could tell something was not quite right. Something's about to go wrong with this system because we now have a pivot here all along. That was our second pivot. And now we move down and right. Our next pivot is over here. But notice how these match up. This is going to cause an interesting problem to occur in our matrix. We only need to eliminate the entry down below. So let's make that row operation happen. The last matrix is going to be row equivalent to. We're going to take and replace our row 4 again. Row 4 is going to be replaced with row 4 minus row 3. So we're just going to subtract these to get the 0 below that pivot right above. This is the unfortunate part of linear algebra. First, a lot of copying. Let me get these out of the way. 1 -6 is 0, 0, 5. 0, 1, -4, 1, 0, 0, 0, 1, 5, 8. And with all that copying, you can see why this is really critical, right? We try to get zeros everywhere unnecessarily. You're really adding a lot of effort to this when you really didn't have to, if it's just about consistent versus inconsistent. Now, next thing, these two zeros here are going to just match up because we're subtracting these entries, but they're just zeros. Now it's row 4 minus row 3. We get a 0 here. It'll be 5 minus 5 again, so 0 here. And then there'll be 0 minus the row 3 entry, so -8, would go here. And as it stands, it might not look too different from the very last problem, but it actually has a major problems going on for it. Anyone see anything unusual about our augmented matrix at the moment? Exactly. If you're looking at this and thinking, well, what are the equations? Something very unusual happened with that very last row. Let's not use that color. Don't want to wipe it out. But this last row has a big problem, like you said. If you imagine reading out what that row says, it's 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4. In other words, 0 equals -8, and this is a contradiction. And from our training in algebra, the moment you encounter a contradiction from a set of equations, it'll tell you you have no solution whatsoever. So because there's a contradiction, this means no solution. Did it answer the question? Well, we're asking if it's consistent or inconsistent. But if you left your work on this page right here, this step, and said no solution, that's okay with me. It's synonymous with saying inconsistent. Let's follow the instructions to the letter just to get used to that wording because the author uses it all over the place. Because there's no solution, we'll say, therefore, little triangle here is just a way to say my big conclusion or of therefore. Therefore, the system is inconsistent. What are we meaning by inconsistent? Well, we mean no solution, but more specifically, you can pick any four numbers for an x1, x2, x3, x4 variable. Any four numbers might solve some of the equations. It might solve three of the four of equations even, but it will never ever solve all four. There's no way to make every single line here completely consistent. Oh, I just noticed I missed the chat. Sorry about that, Brian. Yeah, exactly. That's our contradiction that popped out of that last row. But any other questions, folks, with getting through this one here? Yeah.
So you did, what we found on that bottom row, the 0 equals -8, we could easily have found that. There's a chance to find it, like, if we found it row 2.
Yeah, absolutely.
No, right then, that, like, we don't have to do anymore because that row tells us that it's consistent, right?
Exactly. So it's all about where are the pivots coming in. So if you took the right operations, let me see if I have this here. If you take the right operations and you were able to tell immediately on any row, let's go to this one, that there is a pivot in the rightmost entry of the augmented matrix, you get to say immediately inconsistent. And so that's what this theorem 2 is all about when we get to it in the next section of the notes. It says a linear system is consistent if and only if the rightmost column of an augmented matrix is not a pivot column. So it's stated in kind of the reverse way. But what happened over here? The pivots are here, 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 and there's more. Go down, right to the first non-zero entry, here. So we have a pivot in the right most column. So that's where it goes wrong. If that ever happens, immediately you know the system is inconsistent. Any questions about that so far? Okay, well, this one's a little bit more of a challenging problem only because we took specifically different steps for reasons that don't look very clear at first until we really harp on it and make it something we recognize in the instructions. So watch out for the instructions in this textbook. Our author, in fact, is really very creative in writing problems, probably because linear algebra itself is a rich subject with lots of ways to say the very same thing. If you're ever unsure what the instructions are asking, don't hesitate to write me an email. I'll be happy to clarify. But the author could write the same kind of question in a lot of different sort of ways. So always look for what is the fundamental drive of this. Am I going for the solution set, or are we just determining if one would exist? Well, for our last problem on these notes, here's what we're going to look into next. Let's bring this one up. This one's a little bit unusual because it has a parameter, or you might say variable, inside the system. We're told it's augmented as well. So if you'd like, you could put down a dashed line to convey that. And the question here is, well, different from the other ones, we're not trying to solve it. We're trying to say, what values could you choose for H that forces this to be consistent? Now we know if it's consistent, there cannot be a pivot in the rightmost column. That was a theorem we previewed per the question in class earlier. All we really have to do is get this into an echelon form because we're not told to solve it. We're just resolving consistent versus inconsistent. And also it's kind of inconvenient when you look at this equation. We put down our row operations we're still getting familiar with. If I want to eliminate this 2, well, we could make that happen, but we'd have to take the right multiple of row 1, add it to row 2, you're multiplying by a fraction. It's not too bad, but then H is going to appear in multiple locations. This is one of those problems where working a little bit differently might be a good idea. This time we're going to do a row interchange. The order the rows appear have no bearing on the solution set. So if they're inconvenient to you, it certainly isn't inconvenient on this one, just switch them out. So let's start off by saying, I'll recopy the problem, -4, 2, going column-wise, 12, -6, h -3. Let's start by just interchanging row 1 and row 2. The way I'll usually indicate that is just saying row 1 gets replaced with row 2, and row 2 gets replaced with row 1. So now just a bidirectional arrow to say we're just swapping in that way. So reordering, we have 2, -6, -3, and -4, 12h. You might want a 1 there, and I would understand if you're feeling that way. You might notice there's always been a 1 right there. But if that forces fractions into the problem, it might not be the most convenient thing to do. Let's just leave the 2 right there. That's our first pivot position right where it is. To get it and reveal all pivots, we just have to eliminate that -4. So here's our next row operation. We'll say row 2 is going to be replaced with row 2 plus, what do we have to multiply here to get a 0 below? Just 2 times this entry added to the -4. So we'll add 2 times row 2 to make that operation happen. Row 1 won't change, it's 2. -6, -3. Then working through the arithmetic, this is going to be 4 minus 4 for a 0. Now we have to keep on multiplying by 2. This is -12 plus 12 for a 0. This is -6 plus h, so h minus 6. And at this stage, we're done. Later on, we're going to call this an echelon form because there's a pivot here. We move down and right, and our next pivot is here. Let me take another look at that. Okay, just making sure my arithmetic came out right. Oh, sorry, I missed that chat again. Brian said, where did the -4 come? Oh, sorry about that. Let me see if I can zoom in a little bit better here for what's already written in. Other questions or comments so far?
You have a error in the OR text, the second set of instruction, which is row 2 into row 2 plus
Oh,
2
yeah.
row 2.
Thanks for spotting that. Yeah, that is really wacky. Thanks for seeing that, Joel. Let me fix that one there. That looks like that's going to be my mistake of the week, messing up these subscripts. What we should have said is row 2 gets replaced with 2 times row 1. Again, sorry for those weird mistakes. I guess things happen in triples. That's my third one of that kind. And this is only valuable if you write it down correctly and carefully. So don't do as I did. Watch out for those subscripts. Other questions or comments at the moment? Okay. And yeah, I see what you mean. These negative signs, depending on my level of zoom, can look very hard to actually really spot. I think the PDF can be a little bit worse sometimes as well. But notice we're kind of in the same sort of situation. Our last augmented matrix was inconsistent specifically because the rightmost column in the pivot, or excuse me, in the augmented matrix was a pivot column. That gave us a contradiction immediately. We want to force it to be consistent. And so we're looking for the opposite thing. What would you say has to be the values of h to force the system consistent? Let's write out if h, we need to fill in that part or the dots, then the system is consistent. Anyone see what we should say right here about H? Absolutely. So if H is 6 itself, that's, a new kind of system. That would mean there's a 0 here, and there's only one pivot. That makes this variable right here a little bit special. We're going to later call it a free variable. This system would have infinitely many solutions. And that's some of the content we're going to be exploring in the next section, 1.2. But that's the issue. As long as this is something that's exactly 0, that doesn't happen. You won't get the pivot entry in that far right column, and you won't get the contradiction. So when it said the values, I guess we had to put the S in parentheses to just indicate, well, it's probably not plural, but it could be. The only real value is 6 itself to force the system consistent. There's a problem kind of like that one in the homework as well. So that's why I felt like we should do some of those kind of problems as well in the notes. But there'd be another one like this in the very next section, 1.2. But any questions at all, folks, with the conclusion of these notes here?
So I feel like I'm misremembering something, but I thought if the pivot point was in like the fourth row, it was like inconsistent, or if there were infinitely many solutions, I guess.
So actually for the infinitely many solutions, it happens to be if, let's see here, at least one free variable is what gives you the infinitely many solutions. So that would mean a whole column, not the rightmost column, but one of the columns from the matrix, the coefficients of the system itself turns out to be all zeros. So that would happen with, say, I don't think we have a system there. And we don't have a system. It's going to be this one, I think, or potentially. The problem is they don't start off with all zeros when I write them down. But what it comes down to is, let's just change this one just a little bit. If this one looks like this, 0, 0, and I guess we have to change a little bit more too on this one. If it looks like this one would be a completely consistent system. You would have an equation for x1, an equation for x2, and no constraint whatsoever on x3. X3 can take on any real number whatsoever. And that's what directly leads it to having infinitely many solutions at that point. Does that make sense with your question there? Gotcha. Other questions or comments at the moment? Okay, well, we got through it, folks. This is the first section of many. Let's save this up for section 1.1. After class, I'll have these notes uploaded onto the Canvas webpage. And that means the due date right here for September 4th on assignment 1.1 is now official. The moment the notes are complete at 100%, the due dates are official. And that means this one's probably a little bit aggressive. I had a feeling it would have been at the start before class today. But these due dates are always going to be in flex. We'll finish section 1.2 when we come back next week on Tuesday. But we have enough time to get started about it. And, we've kind of really looked at some of the main content already with what's going on. Another thing that happens is the Canvas is in flex too. If we have to move things down because we're finishing it in the next week, we might not always do this in class, but this might be something you see when you come back to take a look at it later. I'm always going to move the notes so they stay on the week we actually complete them, not necessarily the week that we looked at them first. And then we're just going to repeat this pattern verbatim week by week by week. So you'll always have a good idea where things are or where things are going to end up. But here's the next set of notes. Starts off with a block of text right here. But it's kind of a review of what we've been doing all along, just a little bit more vocabulary to make things formal. In fact, we've been saying pivot position, pivot column all along. And so we're just at a good position now to actually literally define these things as we go. Section 1.2 is kind of a redo of section 1.1. It's just broken up because there's a lot of vocabulary to try to throw into one single section. So what we're looking for is that nice staircase-shaped type pattern. That's what's revealed as an echelon form. And the echelon form is going to tell you if your system is consistent or inconsistent. So this determines consistency for us. If you want to know more, if you want to actually solve your system and get the solution set, you need row reduced echelon form. You know, that's not a bad comment to throw in right now. Let's put this in just to reinforce what we said earlier. So echelon form, I think we used this color. This form here determines consistent versus inconsistent. And for a whole lot of questions in linear algebra, that's all you want to really know about. Sometimes we go a lot further into the so-called row reduced echelon form, and this is going to determine the solution set. So purpose of example 1 is just to tie together all this terminology all at once. Let's start with echelon form because row reduced echelon form is just a further on reduction from echelon itself. So this is what we want. 3 conditions. All non-zero rows are above any row of all zeros. So let's take a look at that. We're looking at rows of all zeros. It's said a little bit differently. My zeroed out rows have to be in the bottom. I typed this out verbatim of how the author wrote. Sometimes I think it's kind of a confusing way this is written. So we're just insisting zeroed out rows land in the bottom. So that works here. This has no zeroed out rows. Neither does this one. This row is all zeroed out, so it's at the bottom as well. So far, no problems. All 4 matrices could be potential candidates if echelon form. Turns out one of them is not, so we're going to try to spot it. That's our first requirement. Next requirement is the so-called leading entry. Each leading entry of a row is in a column to the right of the leading entry of the row above. If you're like me, that's a mouthful, right? So let's work through that carefully. Starting with what we mean by leading entry. We start in the top row and circle the first non-zero position. That's a leading entry there. Then we move down, move to the right until we hit the next non-zero entry. That's the next leading entry. This one only had 2 leading entries, and what this is saying is, working from the bottom up, a leading entry has to be to the right of the leading entry above. Yeah, this one's to the right of the leading entry above right here. So part 2, I think, is really hard to really see exactly what they're saying, but just get in the habit of what we were doing in all of LAX section 1.1, circle what we'll later on call formally the pivot positions. So on this one, this is a leading entry, move down and right. That's the next leading entry, down and right. The next leading entry, and echelon form, again, is just a way to say a staircase pattern. This goes like this and this for a staircase. This one goes like this and this for a staircase. That seems to fit the spirit of what we mean by echelon. Next critical thing, though, is this one. All entries in a column before leading entry are zeros. So let's look at this next matrix. That's a leading entry. However, this is a problem immediately right down below it. Let me pick out a better color here. Go with that's another leading entry, or excuse me, that's a value below our very first leading entry, and it had to be a 0. Because that entry is not a 0 right here. This is not in echelon form. Echelon's kind of an interesting word. If you speak German or you study German, you'll notice a lot of German is in linear algebra. It's heavily influenced by German mathematicians. That's why we have interesting words like eigenvalues, eigenvectors, just more German. Does that make sense on why these ones are now in echelon and the one below is not. Awesome, we should formalize what we're saying here. So the pivot positions or the leading entries move to the right. All entries below those leading entries are 0. So we'll say that this is in echelon form. This one's in echelon form as well. And how about this one? We haven't really looked at this one too carefully. It's weird, right? This first column is all zeros. Again, that doesn't happen too often when you're writing down a system, because if x1 had no coefficient, and if this is a real application problem, you wonder if x1 should have been part of the model in the first place. They had no leverage. But sometimes this really does happen in certain contexts, so it's an important system to look at. So the first leading entry is going to be this one. We move down and right, that's the second leading entry. We move down and right, and that's the last leading entry. We circle those leading entries, which we'll later call pivots. There's 0 strictly below them. So that tells us this one is also in echelon form. So that's what echelon form is all about. If you can visualize a staircase when you circle the leading entries, and there's also zeros below, you have an echelon form for your matrix. And if these were augmented matrices, we could determine consistent, inconsistent immediately. But let's go on to the next thing. We want to know which ones are in echelon form, reduced echelon form, or neither. I guess I didn't answer these questions perfectly literally. If this is not in echelon form, then that means neither for this one. If you're not in echelon, you cannot be in reduced echelon. So that's an important fact to keep in mind. So reduced row echelon form is just what we were saying we needed when we were solving a system to get the solution set. We need the leading entry in each non-zero row to be a 1. Automatically, this one's out, right? Leading entry here and here are 2s and 3s. So this one is not in row reduced echelon form. Then this one right here, it's in echelon form, but notice there's zeros below. This one has zeros below and above, and also the leading entries are 1. Sorry, I kind of jumped the gun on that one. Leading entries are 1, and then I was thinking of this. 1 is the only non-zero entry in its column. In other words, when you go to the column, there are going to be zeros below, or if it's in the middle, above and below. So this one's not just in echelon form, it's in reduced echelon form. Similarly for this one, if you spot what we indicated identity matrix from the other notes, you're also in reduced echelon form. So the top rows were reduced. This one is not in echelon form whatsoever due to this position, and this position. And this one is off because there's no 0 here and here, but also because of the 2 and the 3. They had to be 1s. Yeah.
So on the second reduced echelon form,
Yeah.
the ones above the leading ones don't stop it from being reduced.
Oh, they do. Good eye on that one. I totally missed this one right here. This one's a problem as per this portion. Right here. Good eye on spotting that one right there. Because of that, this one is not reduced. This one is just strictly echelon form. So that right there wiped out the reduced on this one. Let me eliminate this so the notes don't get too busy. Does that make sense to folks on the problem right here for this one? Okay, I was saying identity matrix, but I missed that right there. That prevents it from being the identity. Had to have zeros above and below, all leading entries. So that's the name of the game of what we're going to study when we come back next section, in section 1.2. It's kind of a shorter section, so we'll also make some headway into the section 1.3 as well. But any last questions or comments, folks, before we call today? This looks like a natural stopping point. Okay, well, if you have any questions about the class, I'll be happy to help out. I have office hours that are going to run from 4:15 to 5:15 every day in this classroom and over Zoom at the same time. So feel free to drop in, ask questions in either way you'd like to hang out, and I'll be happy to help. But otherwise, have a great weekend, folks. Enjoy the Labor Day holiday that's coming up. I'll see you all in September. Thanks, you too. Thanks for spotting all those weird little issues on there. You have a good eye. Yeah, I hear you. You too.